Good morning all. In this video lecture we are going to discuss the topic estimation of no load current of transformers in the subject design of electrical apparatus from second unit design of transformers. Uh, you can say that estimation of no load current of transformers is what we are going to discuss now. Estimation of no load current of transformer. Actually, the transformer under no load condition, it will draw no load current only from the source, and this no load current has two components. One is magnetizing component, another one is iron loss component. The magnetizing current depends upon the MMF required to establish the desired flux, and the loss component will depends upon the no load current, depends upon the iron loss. Okay, so this is the dimension of core type transformer core, and so this vertical dimension is the length of the core, and this horizontal dimension is the length of the yoke, and this length of the core is also equal to height of the window, and the length of the yoke is also width of the window. And MMF, we are going to calculate now the magnetizing current first. And to calculate the magnetizing current, we are going to calculate the MMF required for core and yoke separately, and then we will be calculating the total magnetizing MMF. So MMF for core is MMF per meter for maximum flux density in the core multiplied with the total length of the core. So this is MMF per meter length. AT is MMF per meter length, and it is for the core. So it is ATC. Multiplied with total length of the core is 2 times of LC, and so it is 2 ATC LC, and MMF for yoke is MMF per meter length of maximum flux density in the yoke. So it is in the yoke, so this MMF per length AT for yoke multiplied with total length of the yoke is at top and bottom sides of the core, it is 2 times of Ly, so 2 ATY Ly. And total magnetizing MMF AT naught, that is equal to MMF for core and MMF for yoke plus MMF for joints also. So maximum value of magnetizing current is it is AT naught divided by TP. AT is ampere turns. If you divide this with the number of turns, you will be getting the current, magnetizing current. Okay, so we are getting the magnetizing MMF. So in that the current is magnetizing current, and T is the number of turns, and at the primary side it is number of turns at the primary side. So suppose usually we will be studying about the transformer with sinusoidal supply, which is what we are utilizing in the power system and grid side and utilization side. So it is sinusoidal EMF. So the peak factor for sinusoidal EMF is square root of 2. So this is the maximum value of magnetizing current, and RMS value is maximum value divided by root 2. So it is AT naught by root 2 TP. Suppose if the waveform is not sinusoidal, it is non-sinusoidal, means then peak factor for the corresponding shape of the waveform should be substituted instead of root 2. Root 2 is only for sinusoidal EMF. So general equation for magnetizing current is AT naught divided by KPK, that is peak factor, multiplied with number of turns. So the values of ATC and ATY are taken from BH curve of the transformer state, and the joints that can be it is actually make a parallel path with the iron path, that will be considered separately. So the loss component of no load current, actually two components, one is the magnetizing current of no load current we have calculated, and loss component of no load current is, it depends upon the iron loss. So it is PA is the iron loss divided by the terminal voltage, that will give the iron loss component, and VP is the terminal voltage at the primary side, and so the total no load current is I naught equal to Im square root of Im square plus IL square, because it is the AC current, so it have both magnitude and phase angle, so we have to consider the vector addition, and so it is I naught equal to square root of Im square plus IL square, magnetizing current plus loss component. This is how we can able to calculate the no load current of transformer. So this is actually for a single phase transformer. The single window has been considered, so it is for a single phase transformer. The same approach can be followed for a three phase transformer also. It is actually core type transformer we have considered in the previous analysis, If it is a three-phase core-type transformer, one more window will be added, so that one more limb will be added, so that it can be a three-phase transformer. Three windings will be there, and all the three limbs of the transformer core. So the total length of the core here is 3 times of LC, and total length of the yoke is top and bottom side, it is 2 times of LY, and actually here LY is 2 times of this window width of the window plus this D. D is the diameter of the circumscribing circle. 2 times of the window starting from this point to this point, and this point to this point is 2 times of width of the window plus this length. So this length is diameter of the circumscribing circle, and so that is the LY, and LC is height of the window. Okay, LC is height of the window, and so length of the core and length of the yoke we have defined in terms of height of the window and width of the window also. Then we will be calculating MMF for the core and MMF for the yoke, and actually total length of the core is 3 times of LC, length of the yoke is 2 times of LY. So here it is 3 times of LC for core and it is 2 times of LY for yoke, and so total magnetizing MMF required is MMF for core, MMF for yoke plus MMF for joints. So this is 3 times of ATCLC, this is 2 times of ATYLY plus MMF for joints, that will be considered as in the previous case. And so the total magnetizing MMF required per phase is, because it is a 3-phase transformer, we are dividing with 3. Maximum value of magnetizing current per phase is AT0 divided by TP, and at the this is the number of turns at the primary side. If it is sinusoidal, then we will be dividing it with the square root of 2. This maximum value of magnetizing current per phase will be divided with root 2 if it is sinusoidal EMF, or otherwise it will be divided, if a waveform is non-sinusoidal one, then we will be dividing with the corresponding peak factor of the particular waveform. So general equation is Im is equal to AT0 divided by KPKTP, and the values of ATC and ATY are taken from BH curve as in the previous case, and then this is the magnetizing component of the no load current, and then last component of the no load current will be calculated from the iron loss of the machine. Being it is a 3-phase transformer, iron loss is 3 times of VPIL, and so it is from this IL we are calculating loss component is PI divided by 3 times of VP. So that will give loss component, so that the no load current of transformer per phase I0 is equal to square root of Im square plus IL square as in the previous case. And this is one way of calculating the magnetizing current from ampere turns and no load current from the iron losses of the machine. Alternate formula for calculating the magnetizing current is from the EMF equation, so it is derived. So you go through both of the equations. So if problems are asked with the different parameters, you can use the appropriate equation to calculate the no load current of the transformer. So here it is the alternate formula based upon the EMF equation. So this EP is the primary induced EMF in a transformer. So the equation for induced EMF in a transformer is 4.44 F into phi m into T. Phi m is nothing but flux. So that is expressed in terms of flux density and area of the iron. And so magnetizing current, the formula is known AT0 by root 2P, and magnetizing MMF, so AT0 is MMF per meter and length of the flex path in the iron. So magnetizing MMF per meter is ATM, and LI is length of main flex path in the iron, that is LI. So weight of iron is volume of the iron multiplied with the density of iron. Density of iron is 7.8 into 10 to the power 3, and so it is density multiplied with this volume of iron. So this is weight of the iron is AILI multiplied with 7.8 into 10 to the power 3. So magnetizing current, volt ampere is volt into current, so it is V into AM, and that is also equal to EP into IM. And magnetizing volt ampere VAM is equal to EP is the primary induced EMF, and IM we are substituting the equation is AT0 by root 2 TP for a sinusoidal EMF, so that we are substituting everything in this equation, and finally this TP and TP will get cancelled from the equation, and this root 2 here, and all parameters kept as it is. and then we are substituting for this 80 knot in terms of ampere turn per meter unit length and the total length of the iron. So 80 knot is equal to ATM, magnetizing ampere turn per unit length and total length of iron. And so we are substituting this value, and then we are taking this ATM outside and we are clubbing this AA into LA, that is volume of the core. And so magnetizing volt ampere per kg of iron is magnetizing volt ampere V AM divided by weight of iron. Weight of iron is AA LA into 7.8 to 10 to the power 3. So that we are substituting those equations, and we are reducing, will be this AA and LI will get cancelled, and after calculating this constant values, finally we will be getting 0.4, approximately 0.4 F into BM into ATM into 10 to the power minus 3. So from BH curve or from the manufacturer's supplied magnetizing volt ampere per kg B characteristics, we will be able to calculate the magnetizing current. Okay. So that magnetizing current will be magnetizing volt ampere per kg, and magnetizing volt ampere per kg divided by voltage will give ampere. Magnetizing current per kg it is weight of the core. So we will be getting magnetizing current for number of phases, and if you divide with the number of phases, that will give per phase magnetizing current per phase. So this is how we can calculate the magnetizing current, and then last component we will be calculating. So by knowing magnetizing component and last component of the transformer, we will be able to calculate the no load current. So in this video lecture, we have discussed method to calculate the no load current of the transformer for a single phase coated transformer, and for the final equation we got is magnetizing current 80 knot by kpk into tp, and last component is iron loss divided by rated voltage at the primary side, and this is the no load current is the square root of IM square plus IL square. And for a 3-phase transformer, so we have added one more window and core limb. So finally we got the expression for calculating the magnetizing current as well as last component of no load current, and then finally we have calculated the no load current of 3-phase transformer, and finally we got an alternate expression to find out the magnetizing current, and that will be in terms of ampere turn per meter of this magnetizing path, and from this BH curve supplied by the manufacturer, and from that we will be finally calculating magnetizing current per phase for the given transformer. Okay, so this is about calculation of no load current of transformers. Thank you for watching.